All right, folks, welcome to our next installment of the Omfit tutorial. Today we have Jeff Lest. He's going to talk to us about the Transp module. A bit of background about Jeff. He's currently a research scientist at GA, but went to University of Washington as an undergrad, Princeton as for grad school, and UC Irvine as a postdoc. So, Jeff, thank you. Take it away.
All right. Yeah, we can get started. Just for some context, like a couple years ago, I didn't know anything about Transp, but now I know something. So maybe you can also know something about Transp. So let's get to know Transp. I'm going to give like 5 minutes of slides, and then it'll be a demonstration. But when I was first told that I was going to use Transp, I didn't really know what it was other than a black box that people used sometimes for some things. So what is it? It's often called a 1.5D tokamak power balance or transport code. It was developed by PPL, I believe, since 1979. Right, so it's 1.5D in that you give it a 2D equilibrium. Of course, the tokamak's axisymmetric, but then the transport solver is done in one dimension. So everything is flux surface averaged. Transp is not the only game in town. There's lots of codes that take a similar approach. You might have heard of 1.2, FastTran, Astra, or I'm sure there's lots that I haven't listed. I don't know if any of them are better than the others. Often you just use whatever the people around you use. Mostly Transp is used to help interpret experimental data, to calculate transport coefficients or things of that nature. It could also be used predictively. So often people say that Transp is an integrated modeling tool. Also, it's not just for D3D. Transp has been set up and is often used for NSTXU, MassDU, East, and I'm sure lots of tokamaks that I haven't listed here. But also, it's important to know what Transp is not. And so it is not a high fidelity first principle simulation code. So if you want to know, really what's the secret of Elms, probably Transp isn't the thing to use that for. The other thing that Transp is not it's not open source. So it's totally controlled by PPL. You can't look at or touch the source code, which has pros and cons. That means you don't have to fix anything, but also means if something's broken, you have limited ways to figure out how it's broken. I believe that Astra is an open source type one of these. I don't know about the rest of them, but depending on what you want to do, that might or may not matter. The other thing to know is that Transp runs on the PPL cluster. It does not run on Iris or Layer or wherever. And so where Omfit comes in is that it really streamlines the preparation and submission of Transp runs. So as I'll show you, there's kind of 3 main inputs for Transp. There's a big Fortran name list called tr.dat. There are these things called U files, which contain all of your experimental data that you're going to pass into Transp and also the equilibrium. Though this tutorial will be outdated next year, I think, when this switches to IMAS format. And there's also templates for physics modules like Torre or TGLF if you're using something like that. The good news is that Transp runs on a dedicated partition of the PPL cluster. So in my experience, you basically never have to wait in the queue at all. Your run will start immediately. But you do need a Transp account to submit runs. So if you're interested, you can just email Transp support and they will hook you up with an account. Once your run is complete, the results are stored in an MDS plus tree and also a CDF. And conveniently, the Omfit Transp module will fetch and plot the outputs very nicely for you. So here's Transp in a nutshell. This makes sense, right? Okay, it doesn't make sense to me yet. So let's start with something simpler. Suppose that fundamentally Transp exists to calculate transport coefficients from your data. So suppose you have some generic conservation equation for some quantity X. This could be density, temperature, whatever. So to run Transp, you need to actually provide all of the input data. So maybe your Thompson scattering data or whatever, but or you could make it up. It could be fictitious, but fundamentally you are inputting, your temperature profile or your density profile. Transp is not predicting that unless you use the predictive Transp. And then the right-hand side contains all of the sources and sinks. So these could include the radiated power, which is input data. It could mean the power deposition from neutral beam, or it could mean ECH or whatever. And so inside of Transp, there are models which take in sort of operational parameters. What's your beam geometry? What's the power over time? And then it uses those models to calculate the sources and sinks. And so then, of course, we have the thing left in the middle, which is the flux, and that is fundamentally what Transp is solving for you. If you already know how to solve for this, then you can leave. You don't need to use Transp. But this is the main purpose of Transp, where this flux is related to some transport coefficient based on some diffusive assumption, and fundamentally you care about this transport coefficient for some physics reason. So that's kind of the purpose that Transp exists, and that's all folded into this type of diagram from Brian Grierson. You could also go beyond just calculating transport coefficients. So you can, instead of giving the Q profile to Transp, you can say, evolve the current forming resistively. And this is, for instance, what you would use Transp for in a kinetic E-fit workflow. You can also say, instead of inputting a magnetic equilibrium, you can have Transp use one of its internal equilibrium solvers to actually solve for a self-consistent equilibrium at each time step. And then the most advanced thing that you can do with Transp, in my opinion, is that you can actually predict your kinetic profiles using reduced models. So for instance, instead of passing in the electron temperature, you could say, Transp, tell me what you think the electron temperature is going to be as a function of time, such that it is consistent with all of my other inputs, and taking profiles from some turbulent transport model like TGLF or MMM or anything else that's in there. This is a notoriously hard problem because basically you're solving some stiff transport equations that are just numerically challenging. And so your mileage may vary here. And if you want to use Transp for this purpose, you first want to find someone who has experience with that to kind of teach you how to do that, because this tutorial probably won't really get into that. And then I have a couple other slides that maybe we'll get to at the end about what do you do if your run crashes, how do you troubleshoot that, and then other documentation. You'll see Brian Grierson's name show up a lot in these slides. I learned from his resources, and all of these bullets are links where you can find other documentation, or the previous Omfit tutorial is really good. You could just watch that also. All right, so now into Omfit. Hopefully this is legible. I made a project to start just so we had something that worked. But of course, if you don't know how to use Omfit, you go to File, and then Import Module, and then you wait. And then of course you could, find Transp and load it, but we won't do that since we already have that. So like any other module, you'll double click on Transp to bring up the GUI, and we'll make this bigger. It's a pretty, well, I was gonna say it's a very big GUI, but I guess there's just a lot of empty space where it's so magnified. Anyways, starting from the top, you'll see that there's a entry for the device. So if we're interested in E3D, this is E3D, of course. You need to put in the shop number. And then the times, actually, you only really need your start and end times. So let's say we were going to analyze between 1,000 and 2,000 milliseconds. And then the other thing you need is a Transp run ID. So your run ID is the shop number, and then a letter, and then 2 more numbers. This is what labels your simulation from anybody else's. So there is a finite number of these, but if you're running out of numbers and letters, then that's very strange. And then the GUI is going to change based on whether this run is one that has already been completed or if it's a new run. And it knows that by talking to MDS Plus and seeing if this run ID already exists there. So this is a shot that I have run Transp for, and I've used this run ID already. So that if we scroll down in the GUI, you see that the first thing it says is, well, what do you want to plot, basically? And so this is a good way to kind of get to know what Transp might give you as an output. So you can select which type of data you want to plot. So there are scalars, there are profiles that are functions of time and space. And then there are also these things called multiplots, which are intended to be some useful combination of quantities that lots of people might want to look at. But just to give you an example, so then there's a question of, well, how do I know what the output names of the transfer variables are? And that's a good question. And unfortunately, there's not like a super great glossary of those, in my opinion. But nonetheless, there is this search feature where I say, okay, what if I want something to do with energy? And then you can see anything that has energy in its tag or its point name will come up. So that is helpful. I'd say it's still, you may want to, if you know that there's something you want to look at, you may want to talk to someone who's used Transp for that before to figure out what the relevant outputs are. But okay, let's say we want to look at energy and we want to look at the energy confinement time. So I'll look at tau EA, and then right away I can just plot this, and okay, there's the energy confinement time as a function of time in the shot. Great. You can do that for any scalar quantity. Of course, you can also look at any profile. So let's say I want to look at, I don't know, let's see, I think this one is the energy heat, yeah, the electron heat diffusivity. So that's something you would use Transp for. And since it's a profile, you have the option of, well, do you want to make a 1D plot that is sliced in time or sliced in space? So let's say you want to slice it in time, and then by default, it'll give you all slices, or of course you could use any Python to pick out specific time slices you want here. But let's just plot, and it'll make a nice plot, hopefully. Yeah, so there's a heat diffusivity. In this shot, there's a spike at row 0.2 because we had VCH aimed there. So of course the power has to diffuse outwards a little bit there. And then an example of the multi-plot. I don't use these that often, but some people do. So let's use the search and see if there are ones that are related to energy. Sure, let's see what energy confinement gives us. And typically these will be like a collection of plots that are related to some type of analysis you may want to do. Yeah, usually red text is an error message, but sometimes people also just use it to get your attention. I believe this message would have come up when I changed the times at the top of the GUI, just to alert you that since you change the time, it's going to load a new name list by default. Okay, yeah, so there are some plots, and I guess this multi-plot shows the electron energy confinement time, the carbon ion energy confinement time, and then the plasma energy confinement what we look at. Very different one. Yeah, so I think one of the strong points of the Transp module is that the GUI is pretty useful for visualizing a bunch of outputs from Transp, especially if you're a new user and you don't necessarily know, well, how do I get the data? This module really abstracts that away and makes it pretty easy. Let's see if there's anything else I wanted to say. Yeah, so like any other module, there are question marks, which usually supply helpful information. And yeah, definitely use those if you're not sure what to do. So one way to plot things is with this run plot sub-GUI. There's also this tab called rplot. I don't quite know the history. I think this is a Transp plotting utility that also talks to, but this is a kind of more, I think you maybe have a few more options about how to plot things in here. And here the question marks are very helpful in terms of telling you like, what is the server that I should put in depending on the device? What's the tree name, and other helpful things. But otherwise, it's somewhat similar to the first tab in terms of plotting things where history is going to be a scalar quantity, profile is time and space. And then these other options are more like multi-plots, I would say, where they're kind of like specific bundles of plots or some specific plot. that may be already massaged a little bit. Some of these work and some of them don't, is what I'll say. And I think that is an accurate statement at all times. Yeah, so that's kind of the plotting features in this GUI. And so now let's talk about, well, what if you want to submit a run? So please don't overwrite, a run that already exists. And you're actually not allowed to do that. So if you try to submit a run, you would get an error immediately. And so then you have to find a run ID that's available. And so one way is you can just guess. But there's a nice tool in the GUI which will get the next available run ID. So it'll look in MDS Plus for everything with this letter J until it finds one that hasn't been used. It turns out that is J11, J1 through 10 are taken. And now that we have switched this to a run ID that is available, you'll see that the GUI is now looks different than it did before, where instead of giving you plotting options to start, it's giving you a series of steps for setting up a new run. And yeah, one thing that I wanted to say that I didn't before, these times that you put up here, you should think of these as the whatever time in the shot that you actually care about the physics and you want to analyze. But then the GUI is by default actually going to set the simulation time to start a couple hundred milliseconds before your start time and also end a little bit after the end time. Starting a couple hundred milliseconds early means that the fast ion density has time to build up, because in your real shot, maybe your beam was on at 500 milliseconds, but the simulation doesn't know anything about that. And so the simulation has the beam turning on when the simulation starts. And so you need to give it time basically to reach the steady state that actually existed in the experiment. And with the output being, you want it to be a little bit later than you actually want to analyze, because Transp may not give you an output time point exactly at your final endpoint. But that's all taken care of for you automatically. So you can see that there are these numbered steps for setting up a Transp run. And indeed, you can get pretty far just by blindly clicking these and not thinking about it. That might give you a valid Transp run. But let's explain a little bit about what's happening. So the first step is that you will load a Transp name list. And there will be some messages in the console while you're doing this. It's always a good habit to pay attention to what's happening in the console. I know that it can be overwhelming when you don't know a lot of what it's telling you, but over time you will understand more and more of it, and you'll find that it is in fact very helpful. So once we have loaded that name list, you'll see that we now have something in the inputs. And so this is, well, each of these are sub name lists. Oops. Where basically this, so this is the tr.dat file that I referred to earlier. And these are, it's a Fortran name list, and these are all the controls that control how Transp runs basically. So everything you need to run to instruct Transp how to behave is contained in some variables in here. And these are populated with default values that somebody has vetted. And so this is another really useful feature of the module that you don't have to think, well, what do I want for this, FNE min? Should it be 1E12, 1E13? What even is that? Somebody's already thought about what a sensible default value is. So let's see. Let's bring the GUI back up. So yeah, that's a pretty trivial step. The next step is that you need to give Transp some equilibrium. And you have two options here. One is that you can just pull from some EFIT that exists in the tree. I'd say this is a pretty common thing to do actually. So for instance, you could choose EFIT02 and then you just say load, and then it is going to talk to MDS Plus and pull those files within the start and end times that you requested. And then is going to run a Transp utility called scrunch, which is going to basically translate them from EFIT format into whatever Transp wants, which is Fourier moments, I think. But let's say you spent a long time making a really nice kinetic efit, and you want to use that as your the start for your transp run. You can also do that. So you see that there's this option to link to an Omfit module. And so I already loaded an efit time module, so it's not a kinetic efit. But if instead of just pulling from something that was already existing in MDS Plus, you could link to the module, and then you could load from there. I think this works for efit time, kinetic efit time, cake, and maybe other things. But basically, as long as you have outputs that are look like the outputs of an efit type module, then it should be able to grab these. So then we can, once again, look at our tree and see what's been populated there. So now we didn't have anything in U files before. So now we have all of these U files. Like most things in Omfit, if you double click on them, you'll get some sort of plot. So let's look at the CUR one. So this is the plasma current in amps. So you can see what that was for the shot and what's being fed in. I'd say these names are not very descriptive. These are just the suffixes of the U files. But another nice feature of Omfit, of course, is that things are somewhat annotated. So you can probably poke around here and find some label. Yeah, plasma current, right? And that's the same for the more questionable ones, like, what is GRB? And there's also 2D input. So here's the cube profile that you input from equilibrium. Just like any other Omfit object of this type, you can drag and average and have all those bells and whistles. Yeah, the U files are also, in principle, you can write a U file yourself outside of Omfit, but Omfit abstracts all of that work and writes it in the format that Transp will actually digest, so you don't have to reinvent the wheel. Okay, so Transp GUI. So we've now successfully completed items 1 and 2. The next piece of information you need comes from the plasma profiles. So here, the default option for D3D is to just pull from ZipFit. That usually exists. And so once again, you can just load from there. Or you can link to a profiles module. So I don't know all the ones that are supported, but I believe Omfit profiles, QuickFit, probably GA profiles are all supported. And if they're not supported, then you could pretty easily write an interface by copying what exists. So we can link that module. I previously made profiles for this shot, so we wouldn't have to wade through it. And then you can load the profiles, and you get an error, which is part of the Omfit experience. Yeah, I don't know clearly that's a mistake on my part of the Omfit profiles. So let's just load the ZipFit instead. So then you can unlink that module and load from ZipFit. All right, so then once again, let's take a look at our tree and see what that actually did. These are also going to be under U files, but now these ones have somewhat more descriptive names. So this is the electron density profile. And yeah, nothing too exciting there, but basically we now have everything fetched in terms of our experimental U file inputs. Let me just see if there are any options there. Yeah, so once you have loaded your U files, you'll notice this tab, view and modify U files. So instead of mucking around in the tree, you could also use the GUI to take a look at some of these files. I guess in principle, you could add some time smoothing automatically here, preview it, and then decide if you want to keep it or not. You could click these buttons to plot all of your different U files. I'm not going to do that, but you could. And there may be some U file options. Yeah, to be honest, I haven't used these ones, but I guess they're here. So yeah, we have now gone through steps 1, 2, and 3. So we've loaded the profile U files, we've loaded the equilibrium U files, we have a default name list. And then there's this very important button, which is the device specific inputs. So I said that Transp can be used for lots of different tokamaks, D3D, NSTXU, whatever. And all of those have different neutral beam geometries, energies. Some of them have BCH, some of them have ICRH, whatever, different recycling. And so this button is basically going to load your heating and current drive actuators, all of the information that Transp needs to use the models to calculate those sources, and also probably set up some other device-specific switches in the name list that are the sensible defaults for D3D versus K-star versus whatever. And so again, this is very nice that you don't have to worry about what are all of these things supposed to be. And once again, this is a very good time to pay attention to what is actually happening in the console, if possible, because there could be useful information here, like, all the gyrotrons are off, which maybe was true or wasn't true in your experiment. Or, yeah, you can see here's an example of me using red text for something that's not an error, but maybe something you want to pay attention to, which is that I updated the module to pull the helicon information to know if Transp needs to run generator or not. And if it doesn't find the power above a certain threshold, then it's going to disable that. So if that's not what you're expecting, then you might want to pay attention to this. So that loads all the device-specific information. And so now in the tree, that might load, yeah, it loads some more U files. So this is like the power over time for the ECH power. This is the power over time for all of the different beam sources, and also like the fraction of power in the different energy components of the beams. And then I think we also have something new in the tree that we didn't have before, which is this templates subtree. So there's 3 pieces of information that Transp needs to run. It's the big tr.dat name list. There are the U files. And then there are also these templates that are used to tell Transp how to run, how to interface with some external modules like torray or genray. And so these will all, or sorry, that won't, I showed you the wrong spot. That's not here. That is under inputs, actually. Inputs, and then this new torray.name list we did not have before. And so that has the information to run torray. So right, we've gone through the first 4 buttons. And then the last, I'd say semi-optional button is that you can set a Transp mode. So maybe you have the device-specific settings for D3D, but of course, different people are interested in different things, and you may want to run Transp differently. So these are basically some preset changes that you can make to the name list, depending on how you want to run Transp. So BEAST stands for between and something shots. It's basically supposed to be in between shot analysis. So it's like, how fast can you run Transp in 20 minutes and get something that might inform you in the control room? I don't think that's being triggered in between shots now, but in principle, you could run that. There's this analysis mode, which is like kind of default settings that you might start with. There's this kinetic EFIT mode, which I believe is what would be used in a kinetic EFIT workflow. This is what evolves the current profile resistively. That would then give you a constraint for your kinetic EFIT. And then these bottom ones are if you want to do some analysis that involves needing to know the fast ion profile with much higher fidelity than you usually would. So maybe you actually care about what the distribution looks like, not just as a function of rho, but actually as a function of velocity and pitch. And so then these 2 are basically going to crank up the settings on the fast ion deposition model to give you that analysis. So you could ask, well, why don't you just do that all the time? Of course, there's always a trade-off between fidelity and time cost. And it turns out that the fast ion model is one of the most time-intensive parts of Transp, because it's basically just a Monte Carlo code. It's launching a bunch of particles, following them around, and then getting a distribution. It is parallelizable, so you can ask Transp to use 4, 8, 16, however many CPUs. But still, if you don't need all that information, then you probably don't want to run Transp that way. When you press this button, though, it's going to change a whole bunch of things in your name list. So, if you made some changes yourself and then press this button, they may be overwritten. And so this is a good time to talk about all the other things you can change, not just using the default and pressing the buttons. So I'd say pressing the buttons is a good place to start. But the next step is to go to this tab that is input name list. And so this has subtabs, and basically each one of these boxes is going to correspond to some item in your name list, but actually in English instead of some convoluted name for a variable that you don't know about. So if you do want to change something, maybe you want your outputs to be output on a finer grid. You can edit that, and then very important, you need to press enter to apply the change. And you can go through all of these things. So for instance, in this shot, I think we were actually modulating the ECH power. And so if you just leave your ECH on constantly, maybe you don't care how often you're calling Torre, but so that I resolve the modulation of the power, maybe this also needs to be smaller in my shot. Or maybe your beams need to be called more often or less frequently, whatever. So it's kind of good practice to go through all these tabs, change the number of zones in your simulation. That's the radial resolution of the transport grid. The most important ones I would say are in the heating tab. So for instance, this is where you can change the settings for the neutral beam. You can see there are these predefined options. You can just choose low, medium, high, or blip, which you can think of as extra high beam fidelity. Or if you want to live dangerously, you can become an expert user, and then it will give you an option to change very specific trans variables. The nice thing about changing things in the Transp GUI instead of changing things directly in the tree, which you can also do, is that there could be some variable dependencies. So it could be that if you set one variable to one option, it doesn't really make sense if you have another variable set to something that conflicts with that. So the GUI ideally has the logic built in to prevent, if I make a change here that, for self-consistency's sake, requires some other variable to also be updated, the GUI is going to take care of that for you. Whereas if you do it in the tree, you're kind of on your own, which can be totally fine if you know what you're doing, but really hard if you're just getting started. Let's see. Yeah, there's also useful plots here, so we can see like, well, what am I getting from, I guess the experimental data? What am I passing into Transp? So here's the beam geometry, more beam geometry. Here's the power over time. Basically, you just do like sanity checks to make sure that things look the way you think they will be. And you can do the same thing with the ECH. You can, well, this will tell you what powers you're programming and stuff, but you can also plot it and see what the aiming was, where the resonance was, until you get an error, which again, normal Omfit experience. Yeah, I haven't encountered that one before, but there are plots that do work. Let's see if there's other tabs that are worthwhile to go through. There's some cool things, like there's a synthetic MSE diagnostic in Transp that you can just turn on, and then you can, especially if you're resistively evolving the current profile in Transp, then it will use the synthetic diagnostic to tell you what you should have seen on MSE, and then you can compare that to what was actually measured on MSE in your experiment, and then make sure that whatever Transp gave you is in some way consistent with what was actually measured. There's a sawtooth model you can prevent Q from going below 1, which otherwise Transp wouldn't know about. So no specific thing here. I would say, you need to walk away knowing exactly how to use this model from this tutorial, but you would want to walk away from this knowing that Transp has a whole bunch of bells and whistles, and some of them may be relevant depending on what your studies are. Like any other complicated modeling tool, the best strategy is to find someone who has used the tool for some type of analysis similar to what you have done before, and then get the best practices from them, and then ideally write them down for somebody else so that it doesn't have to all be oral history. Okay, so suppose you are satisfied with, you've made some changes here, or at least you've checked out things are kind of the way you want them to be. So now we're all set up to submit our Transp run. And then there's one last step, which you need to provide a meaningful comment. So let's say this is Omfit tutorial, please work. And then you're going to press this button to prepare the Transp run. And so that runs a utility called tr start. Basically, this is going to bundle all of the inputs together and get them ready to be sent over to PPPL, which is where the code runs. Conveniently, if you prepare your run through Omfit this way, all of your input files, in addition to being in your project, are also always stored in a consistent place on Iris/Omega. So they will always be in Fusion project code, Transp, your username, and then your run ID _temp. So we can look at the one we just made, 209 J11. And so here are all those U files and the tr.dat. Although these have a temporary name, I've never seen these purged. So I actually use this as like a nice archive to, if I ever want to, look at what the tr.dat was, or if I wanted to use some U file for some other shot. I find this pretty helpful.
Can you do an ls-l? Okay, thank you.
Yeah, they're not giant files, I think. And then the thing that actually gets sent to PPPL, I guess, is this tar file. And so if you just press tr start, the prepare Transp run that's not sent yet, but basically this is, in addition to bundling, it's doing some checks. So if you made some mistake in your tr.dat, or if there's some crucial input data file that you did not provide, this is going to fail, and there will be some error message here, but this worked, it ran successfully, it created the tar, and so then the last step is that you would submit the run with this button, and so that is going to submit the run to PPPL to run for you. Right, and you do need an account for that, and you can get that account by emailing Transp support and asking nicely. The other thing I should mention while this is going is that suppose you clicked prepare your Transp run, it finished successfully, and then you're like, oh wait, I want to change something. I want to change the beam power or whatever. You go into the GUI, you change it. You'll have to run tr start again because that change will not be propagated into the bundle that was created. Once you get to this screen, I believe you can just abort because once again, this is not actually executing anything. It is just sending something to the Transp grid. So I think we can just kill this, and the run is still fine. If you want to know the status of your run, there is a Transp grid monitor, which I find very helpful. So we could put in my Transp username, which I don't remember, but it has my last name in it. Yeah, and so here's the run that we just put up there. Apparently it is running. And then you can see I have some other jobs that are running, and it'll tell you where it currently is in the simulation, how long it has been. This is not representative. This is a very high fidelity predictive run. I'd say a run like we just made might take on the order of an hour, a couple hours, something like that, depending on how long of the shot you're interested in, how high the new beam settings were. Those are the main things. You only get these crazy long ones if you're running TGLF, and then the adaptive time step ends up becoming very, very short, which is not the typical thing that you will do. Let me see if there's anything else that's really important to cover. Oh yeah, I would say that while there are a lot of tabs in this input name list, it's definitely not exhaustive. These are, believe it or not, a down selected set of variables that someone decided were the most commonly used ones. But there definitely are some Transp variables that are not in the GUI, but you can still manipulate them in the tree. Or there's even some variables that aren't even in the default name list that have some default options. If you don't supply a value, that if you want a non-default value, you could then manually add to the tree. Yeah, also, I don't think I said before that these sub-name lists are organized sort of by topic. But this, I believe, is purely cosmetic for your benefit. Transp does not care at all where these variables live. So, in principle, you can be as messy as you want. But this structure is purely for Omfit. I skipped one thing that was important, and then I'll probably stop at some questions. But let's go back to that run that was already finished. So that was J01. Because let's say the run that we just submitted works, and then you might want to know, well, did it even make sense? What should be your first step in evaluating if your transfer run is garbage or accurate or what you want? So there's this option at the bottom of the GUI for completed runs that is to compare to experiment. And so basically you put in some BFIT that is ideally the same BFIT that you used. If you use a custom BFIT, just pick one that is reasonable. And then this compare to experiment button is going to create a series of plots that compare quantities that sort of check the validity of your run. So this first plot is the neutron rate, and it breaks down a whole bunch of different components. So all except for this measured neutron rate, so all these bottom four, these are calculations that came out of Transp based on your profiles. And so you can compare the total neutron rate that Transp thinks there should be based on the information it has, which is this pink curve, to the actual measured neutron rate, which comes out of experimental data. And so that is this blue curve. So ideally, you would like these things to be pretty close. And then the ratio of them is plotted here. In this case, the experimental neutron rate is somewhat lower than what Transp thinks it should be. A couple reasons this could be, if your neutral density was, I forget which direction, too high or too low, that would affect the initial beam deposition in a way that would create higher or lower fast ion density that would propagate into the neutron rate. Or if there were fast ion driven instabilities in your shot that led to redistribution or losses of fast ions, that's a common reason, especially in high performing D30 shots, that you could have a deficit between the experimental and measured. There is no kind of self-consistent alpha eigenmode model in Transp, but there is a hack where you can put in some artificial diffusion for the fast ions to kind of play the role, as if you did have a model to decrease the beam density a little bit. That's something that people play with to close this gap sometimes. Another quantity is the stored energy, where you can look at the measured energy versus what came out of Transp. And once again, you want this ratio to be pretty close to 1 if your simulation is valid. These last two tabs only kind of make sense if you were actually evolving the current profile, which I did not in this shot. So of course, the surface voltage is tautologically exactly the same as the measurement because that was the input, and same with the internal inductance. But these are all kind of the first sanity checks you might want to make to see if your run kind of made sense or not. I realize I did not tell you how to evolve the current, so that's maybe the last thing I'll do. So let's get a fresh run ID. Right, so one way to evolve the current is, after doing all the steps, you could just set this to kinetic BFIT mode, and that would do it for you. Another way is that you go into this input name list, and then in equilibrium, this is where you choose what type of equilibrium you want. So this is the most common by far. This is saying, I'm just going to give you an EFIT or something. Please don't change it. This option is if you want to have Transp solve for a self-consistent equilibrium at each time step using a fixed boundary solver. And this one is the same with a free boundary solver. But let's leave the equilibrium the same. If you want to evolve the current, you toggle this button. And basically the difference here is that if you give it a Q profile and don't have it evolve the current, then Transp will calculate the resistivity that it infers from the time evolution of the Q profile that you gave it. But conversely, if you say, please evolve the current profile and predict Q for me, then it's going to calculate the resistivity from some physics model based on the profiles that you gave it. And then it will solve a resistive diffusion equation to figure out what the current is at every time. And you can give it different constraints, either say, match IP or match the surface voltage, but let IP be different, or you can match both of them and allow Z effective to be changed in order to satisfy both those constraints. Yeah, I think there's a lot more that could be said about this, but maybe it'd be useful to take some questions. If anybody has questions, like if there's a thing you want to do that you want to know if the GUI can do.
I have a question. With the sawteeth, I was looking at this part here and the menu you showed before. It says that it can arbitrarily go below 1, or it can arbitrarily go above 5, and so you can set limits on those, which means that it's a degree of freedom, right? What is it? Why is it floating? That's a physics question. It is a more than a GUI. What was the question?
So the option to limit the maximum Q probably lives, here. I believe this is more of a numerical constraint that you want to impose, because I think if there's very little current on axis, then Q is going to become huge on axis, and for some reason that I don't know, that makes the solver not happy. And so you usually just put some large number here, 5, 10, whatever, and you will sometimes see it hit this very early in the discharge, but I think it's often inconsequential. With respect to the sawtooth model, I think it's just a choice you can make to say where, at what Q do you trigger this model. There are some people who have ideas that Q can actually go below 1 during sawtooth. I'm not an expert on those. But if you don't use any sawtooth model, certainly Transp will happily send Q lower and lower as the shot evolves, and that will be a discrepancy with the experiment if you had sawtooth. So it's something that people definitely use this model. Yeah. Thank you.
So you mentioned that the beam diffusivity can be adjusted to matching the measured neutrons and calculate neutron. And could you explain how can I do it in the
Yeah. So my guess is that's only an expert user function, but let's verify that. Oh, it's not. Okay. Yeah. So here we are in input name list, heating, NBI, then come to the very bottom. There's this option for fast ion diffusion. Let's toggle this. So I think there's 2 different ways. And again, the tooltips are very helpful here. So one way is that you can just basically guess how much diffusion you need. And so sometimes people would just submit, maybe 4 runs and then just do a scan of, say, I actually don't know what the typical values are here, but let's say 1 makes sense, and they do, 1, 2, 4, 8, and then kind of narrow in and then iteratively look at the neutron rate. If you want a flat profile, then you need to put the same number in the minimum and maximum box, radially flat, sorry. If you supply different minimum and maximum values, then I think it ends up being some sort of multiplier of the electron diffusion rate, the electron diffusion profile scale to those minimum and maximum. But I think in practice, I've seen most people just use a flat profile. The other option is there is this PID controller, which I have not used before, but I think works okay, where basically you're not imposing the diffusion profile. You do give it some minimum and maximum value, but then as the shot runs, it's basically going to use this controller to try to figure out how high does the diffusion have to be to best close this neutron gap. I'd say this is something your mileage may vary. It could work great, but I wouldn't be surprised if it doesn't work out of the box, like just going 1, 2, 3, 4, 5 on the buttons does. But Brian Victor said that he often uses this anomalous diffusion. So I think it's definitely something that people use.
Thanks for the answer scenario. That's really helpful. I understand you have already covered a lot in this trans module, but in my experience, a lot of effort I spend when preparing trans is actually when I'm preparing for the EFIT equilibrium and also the Omfit profile. So is there anything you want to comment on there, like special thing we want to pay attention to when we prepare those things? Like for example, if that's a negative triangularity shot, would you prefer to have a more accurate EFIT reconstruction? Or if that's a LME-H mode, would you like how sensitive the trans output will be in terms of the Omfit profile when you prepare it? Like whether you have a really nice Elm filter or not, like how sensitive they are to those kind of input profile.
Yeah, I would say that's an excellent question. I don't know the answer. To be honest, my impression is that Transp has not been, while Transp has been around a long time, I don't think there have been that many careful studies of, like sometimes people do sensitivity studies like this, but not as much as one would hope for something that's used so commonly. So in practice, I think what happens is, if you are say, oh, I want to get into NT studies, you find, okay, who's done the most transcripts of NT, and then you try to find the advice from them. I'm not saying that's the best, that's how it should be, but that seems how it is in practice. And same with the other scenarios. It's like, okay, maybe you set up a run yourself, but then quickly you find, who's the expert on this topic, who might know. Yeah, in terms of myself, I think I have a lot to learn still about what the best practices are for the EFITs and the profiles. One of the ways Transp can crash can be due to not being happy with the equilibrium. And that's one type of crash that I don't have intuition for how to solve yet. But maybe that's a good segue into what to do if your run crashes, which may happen sometimes. Assuming you don't have a follow-up question.
I don't.
Okay.
Just go ahead.
Yeah, so if your run crashes, you will get an automated email that may or may not be helpful. And so here's, it'll say Transp processing error. And if you run Transp, you'll get a lot of these emails. So I suggest filtering them so you don't pull your hair out. And then if you click on this email, if you click on this email, it'll have some very cryptic text that usually won't mean very much. Sometimes there's an error in here that will be obvious. It'll be like, oh, you didn't include a template, and you can fix that. But sometimes there'll be red herrings. Like maybe you see, oh, this says NBI. Maybe this is a Nubian problem. Often that's not the case. Often, Transp had some stack of function calls, and then, the first error then leads to another error as it, that module exits with some code. But what is helpful sometimes is, let's see, there is a link to logs. And so you can search for your run ID on these logs. And then you can look through these files and see if there's anything useful. Sometimes that's used, like basically see, is there a blatant error that I can understand? Which is sometimes the case and sometimes not the case. If it's not the case, if you have access to the PL cluster, which I find very helpful since that's where Transp runs, you can go to a path like this, of course, put your own username and your run ID here. And then if you look in this log file, you can get pretty far in terms of finding the true source of the error by grepping for error, question marks, and exclamation points. But okay, let's say you don't have access to Portal. Then a very helpful tool is the Transp repository, which is the GitHub where you are meant to interact with the developers. So these are more resources. Each one of these are links. So we can click on the GitHub. And if you go to issues, you'll see a whole bunch of users complaining about problems they had, or even just asking like, this run failed. I couldn't figure out what was wrong with it. Can you give me help? And the Transp developers are quite responsive in answering your questions. I find you'll probably get a response in a few days. And they have, so much knowledge about what's actually happening in Transp. Yeah, like it looks like this was an equilibrium problem. This is super helpful because, let's say one of these files actually did have some error message that you thought might be the problem. Then of course you can, sorry, the Zoom thing is blocking me. Yeah. You can search in here after killing the open tag and then see if somebody already encountered that problem and it's, how to solve it. This is probably the main way that I've learned how to fix transgrounds. If that fails though, it's totally fine to contact your tokamaks Transp responsible officer for D3D. That's currently Sean Haskey, or any other expert user, from your group or something. If you're just like, oh, I know that Wilkie has run a bunch of stuff with lower hybrid. Maybe and I'm running a lower hybrid simulation in Transp. Maybe he knows what this is, or maybe he can point me to somebody. So those are good things to do if Transp fails. And then I'll just leave some other resources. So like I said, the previous tutorial from Brian Gerson is like really, really good. I would suggest starting there. There's a paper that it's based on that's also useful for learning more. There's a pretty in-depth tutorial document originally written by Brian that has since been contributed to other people. This is a good place to kind of go through and check that you understand how to follow along. And let's see, there's links to other devices stuff up here. So if you want to know how to run on Jet, they have good documentation also. This is just the Omfit module page. And then there's other documentation that you can check out for yourself, I guess. But yeah, that's what I have. Oh, Niels.
Is there a way to also directly load A, P, and G files, etc., instead of using the Omfit, EFIT, and profiles modules, because not everyone uses those?
To directly load a G file.
Yeah, as input, and P files.
Yeah, I think the answer is there's no direct way. I would say that so basically you're saying you're opposed to loading them through the EFIT time module, or is that an acceptable?
Say that you use Tom's tools to create kinetic EFITs. You can write the kinetic EFITs to MDS Plus and you can load them here, but what about, for example, the profiles from Tom's tools that are written in P files?
I don't know the answer. I would say however compatible Tom's tools are with profiles modules and EFIT modules, then if you can get them into those modules, then Transp will not care as long as the outputs look in the format that it would get from a normal Omfit profiles or whatever.
I think the answer is, if it's a format issue, then Omfit can handle it. If it's, there's something unique about the format that hasn't been encountered, which Tom's Tools has been around, and we've worked really hard with Tom's Tools to incorporate it. I think you'll be fine just importing those directly. P files should be fine.
Yeah, I recall that sometime in the past, Brian Gerson did incorporate outputs from Tom's Tools into running Transp. So it's in there somewhere. Maybe it's not exposed in the GUI, but maybe there's some scripts that are already set up to do that. Okay.
I'd also say that in general, the Omfit module is a really useful place to get started. But if you ever become, like a power user of Transp, just like other codes, often you may find it useful to start scripting stuff. And then, you can, like Will said, it's purely a formatting thing. You can always write an interface yourself to get what you want to talk to Transp. That may involve running Transp command line utilities, but you can learn how to do that if it's worth your time and you don't want to click GUI buttons forever and ever. Yeah.
One thing I sometimes feel confused about is how to choose the appropriate new beam fidelity. So of course, that depends on what physics you are interested in, but will there be sort of a hard limit on the beam program you apply for the discharge? For example, if you have a fast modulated beam, will the medium fidelity give a reasonable good answer, or you have to go to like higher fidelity even for the bleeps? Another question is, if you have like counter beam, like balanced torque, will there be actual requirement on the fidelity?
These are very good questions again. So I just pulled up, this is the paper from Brian. He covers this a little bit. There's a section about sort of what the sort of purpose of each of the different fidelities are. And he has plots like this to show you, well, what would the torque profile look like for different default settings? And not just the torque profile, but how noisy is, okay, I guess this is still a row slice of that. But he'll also show, how the fast ion distribution function looks like in velocity space with the different settings and how much smoother it gets. So I think, so one answer is, yeah, the faster you're modulating the beams, of course, you need to call new beam faster, with a shorter time step in between calls to new beams so that you don't just smooth out all of that. I think in general, if you just want like diagnostic beams, like once in a while you have a blip for MSE, you probably don't care too much about resolving that. But if it's actually for, let me say this, if you're doing fast ion physics like I used to, I would kind of always just bite the bullet and have the high fidelity model because, we're not talking about, oh, this is going to take 2 weeks. It's like, okay, the run will be done tomorrow. And why not just have, brute force through it and get the really nice distribution function? Because I can't take, derivatives of this, but I can take derivatives of this pretty easily. So I don't know specifically with respect to balanced torque or not. I would definitely take a read of this section. But I think one answer is, you could try it the default fidelity and then look at the outputs and see if it's as smooth as you would think you need for your analysis, and then increase the settings if you want. Like it's definitely not, it's not prohibitively expensive to use the high fidelity thing. Like again, you're gonna go from a couple hours to, maybe 8 hours or something, because you can also use the MPI to use up to 64 cores, and it's, it's pushing particles, so it's completely parallelizable. So I definitely wouldn't be scared to try that. And it's, you're not using up anyone's NERSC allocation. In my experience, the PPL cluster is underutilized for Transp. So your run's still going to start immediately. You're not going to be preventing anyone else from doing physics. You could, use runs that have different fidelities and see what you want. Yeah.
Let's thank Jeff.